Trichtchenko, who's going to speak about computing traveling flexural gravity.
All right, thank you very much. I'm very happy to be here, so thank you to the organizers for inviting me. So I'm going to talk about more computational things, but I'm really glad that Emilian was right before me because he did a good setup of the physical part of this talk, and he introduced some of the models. So this is joint work with him as well as Paul Milewski at University of Bath and Jean-Marc Vanden-Broeck. So I did this work during my postdoc in UK, so it's nice to be back here. Okay. So the outline of my talk. So I'm going to give a little bit of a motivation, but since Emilian covered most of it, that shouldn't be too new to you, and I won't focus on it too much. And I'm going to talk a bit about models that we're using for flexural gravity waves. Once again, Emilian did introduce them, but for the purpose of my talk, it'll be important to, I'll be comparing these different models, so I'll show them again. And then I'm going to talk about what kind of reformulations we use for the equations before we actually start computing solutions. There's a variety of these reformulations that people in the water wave community have, and I'll focus on two particular ones. And then I'm going to talk about some two-dimensional solutions, as well as their stability, or I guess instability really is what I'll focus on. And then I'll talk more about 3D waves and conclude. All right, so what my goal of when I came into this project, into this group, was to try to efficiently compute solutions for different models for waves under ice. I'll refer to these as flexural gravity waves. And my goal was to compare the solutions to the different models. Okay, so here's the schematic. So the gray doesn't really show up, but the water is in gray. We have a sheet of ice and we have air. So this is for the 2D case. And what I'm interested in is actually how the wave profile, so this eta is what I'll call it, how that's going to look under a variety of conditions. So I'm just going to look at surface elevation and how that changes. And so I'll either do this for water of finite depth, where the depth is little h, or I might, in some cases, take h to be infinite. I can do this in 2 or 3D, so either this eta will depend on x, it might also depend on y. And then the other thing to notice, too, is that when I'm doing these computations, I have to either do them for on a periodic domain, so x, this picture will repeat many times, or I have to do this for infinite line or infinite plane. Okay, so here are the equations. Emilian has already showed them to you, but I just have probably slightly different notation. So I'm considering a viscid and compressible fluid. We write this down in terms of the velocity potential. So in 3D, it depends on x, y, and z, as well as time. And I wrote down the forced Euler's equations, because here I have this forcing that is represented as P. And then we have the conditions on some domain omega. So once again, omega is either periodic, and then in 2 dimensions, I'll consider the periodic problem, just because that was more interesting to me at the time. And then in 3 dimensions, I'll consider these solitary waves, so my domain should extend out to infinity. And we have water depth h. And then the important thing is the boundary conditions. So on the right-hand side, this variational derivative with respect to h, where h is some Hamiltonian model. So in most cases, I'll consider a Hamiltonian model for these flexural gravity waves. So that's what will go on the right-hand side. And then d will be the flexural rigidity. So that'll come in as a parameter into my problem. And then we can non-dimensionalize this in different ways. In this case, I'm showing the Froude number, which is related to wave speed and gravity in that way. And then I'll show you kind of what the pressure distribution looks like later. And so in some cases, I'll consider forced waves. In some cases, I will consider it for free, either periodic or solitary waves. All right, so these are the equations. And so in the water wave community, people usually don't go and just solve these 4 equations. They try to reformulate it so that you have less variables to keep track of. And so, all right, so the first thing, let's talk about what goes on the right-hand side. So the term modeling ice will assume that we have a thin elastic plate. So Emilian discussed this already. But the thing that I want to point out is that the ice will bend with the wave. So I'll only really want to look at what the shape of the wave looks like. There's no friction. The sheet is continuous. And so we've kind of already talked about all these assumptions in the previous talk and kind of the downsides of them. So I won't mention them anymore. And then the coefficient of flexural rigidity D, which I'll end up varying throughout the talk just to show you different types of regimes. It's related to Young modulus, Poisson ratio, and thickness of the ice. So that's shown here. And I'll just talk about values of D, and I won't even have dimensions for them. I'll just talk about different regimes later on. Okay, so in this case, for most of this talk, we'll consider two models, and there's different names for these models, but in my case, I'll refer to them as linear model. Even though I say it's a linear model, I still look at nonlinear waves using that linear model, so it's a little confusing, but I'm always computing nonlinear solutions. But I either have a linear model for the elastic sheet, or I'll have a nonlinear model for elastic sheet. And so the nonlinear model is, as Emilian has also introduced, based on that Plotnikov and Toland paper, and so it's based on a Wilmore energy. And so there's a lot of work, and I won't focus on this slide too much. But this work was started probably by Granhill in 1886 and continued by a variety of people. And then for review, you can look at that 2007 paper. And so there's a lot of different models, so there's a lot of different ways to represent that elastic sheet. And then people have been discussing, existence solutions to those models for specific parameters. So either using a Lagrangian formulation, a variational approach, or looking at solitary waves, for example, or looking at periodic waves as well. And then a variety of people have also been computing solutions in 2 dimensions. So for example, Emilian and Jean-Marc, they've looked at generalized solitary waves as well as periodic waves, and Emilian has already reviewed some of what those solutions look like. And Tal and Jean-Marc have also numerically computed periodic and generalized solitary waves using the nonlinear model, is what I'll call it in my talk. And then, so what I'll be doing as well is I'll be looking at numerically computing periodic solutions, but I'll be using a different formulation. And that's based on my PhD work, where we did this for capillary gravity waves. And so to change that to flexural gravity waves, you just have to alter the boundary condition. And so I'll show you that. And then in 3 dimensions, Zan and Paul have done some asymptotic models, and they looked at generating bifurcation diagrams, and they showed that these flexural gravity waves don't come in at 0 amplitude, and Emilian discussed that. And they've been using boundary integral method to compute these waves for the fully nonlinear model. And also, there's been work by people that have looked at small amplitude solutions, so kind of more in a linear regime for wake patterns using Kirillov methods, so using kind of an iterative inverse methods and preconditioning, so using these high performance computing techniques to kind of get to compute on a larger domain, so that they didn't have to compute direct inverses. They can use iterative methods and get larger or get more accurate solutions on larger domains. And there's been several papers on this. I don't have all the references. Okay, so let's look at 2 different formulations. And as I've mentioned, there are many more, and there's papers comparing these different formulations. And part of the reason I'm using the formulations I'm using is not necessarily because they're better at computing waves in 2D or in 3D or et cetera. It's more of the people that I've worked with. So for example, Jean-Marc and his group have been using the boundary integral method, and it's based on the work by Forbes. But when I was doing my PhD, we were using a lot method based on the Abelos-Foucault-Mosamani paper. And so both of these methods have their advantages and disadvantages. They kind of just push these advantages and disadvantages to different limits. So for example, the boundary integral method, you might see appearances of small denominators, and whereas the way that large terms show up, so instead of small denominators, the way that they show up is actually in the exponentials for the Abelos-Foucault-Mosamani method. So there's kind of downsides of both, but there's different ways of dealing with these large numbers that you end up getting. Okay, so the identity behind boundary integral method is using Green's second identity to rewrite your integral, and so you make use of the fundamental solution, which satisfies Laplace's equation. So that's the identity behind boundary integral method. And the identity that that you use to reformulate using the Ablowitz-Fourcault-Mussolini method is actually something a little bit more strange, where if you assume that both phi and psi satisfy Laplace's equation, which is the main equation describing the bulk of your fluid, then you also have this identity, which is kind of not a very intuitive thing to just come out and write down, but that's what happens. And then if you assume that this psi is this exponential in its particular solution, where k is your wave numbers in each dimension, and then you can use the divergence theorem and boundary conditions, and you can rewrite your Laplace equation in terms of a non-local equation. Okay, so the other thing you can do, and this is what Emilian covered, is that you can also reformulate your problem only into surface variables. Since I told you I'm only really going to care about the wave profile, and so I don't really want as output of my solution to be the bulk of the fluid. I just want to know what happens at the surface. I can write down even the velocity potential in terms of the surface variables as well, and then use chain rule, and then get the Bernoulli condition in terms of only the surface variables. And then once again, I left this right-hand side term, which will represent the flexural part of the model, as something general, so you could put in either that linear model or the nonlinear model for the elastic plate. Okay, so let's look at two-dimensional things. Okay, so in two-dimensional case, I use the Ablowitz-Fourcault-Mussolini method. So you can write down what they refer to as the local equation, which is that Bernoulli condition, but rewritten in terms of your surface variables. So Q is the velocity potential at the surface, and eta is the wave profile. And then in 2 dimensions, you can write down what they call as non-local equation. And so here I've written it down for waves of period 2 pi. So you can write it for waves of different period by changing your bounds on the integral. So instead of 2 pi, you can put in a different period, for example, general period L. But if I'm considering waves of period 2 pi, then this k will just be an integer. So in this case, my k will be kind of what represents the discretization. So I'll pick different integer k values, and then I'll I'll solve that system for a lot of values of k. So this almost looks like a Fourier transform, but it's not quite, because you have this exponential, but also hyperbolic cosines and hyperbolic sines. So this is kind of where you can see already the appearance of a problem. So hyperbolic cosine and hyperbolic sine have exponentials, and so you might have things blowing up for large k times eta or k times h. Okay, so this is still hard to solve. This is the time-dependent problem that's still hard to solve. So let's focus on a traveling frame. So let's move into a frame traveling with speed c, and then we'll look at the steady state. So now we've parameterized our problem by the wave speed c. And then we can use the local equation, obtain the derivative of the velocity potential, plug it into the non-local equation, you just get one equation. So the unknowns now are the wave speed, and then the wave elevation. And also I've left that term once again in general, and then d is the flexural rigidity. Okay, so the linear model that we'll plug in will just be 4 derivatives of eta. And the nonlinear model, Emilian has already shown this. And so this is just in terms of curvature. So this is 2 derivatives of curvature, and this is the curvature cube. And so we'll plug in that right into there. Okay, so I mean, it's just long, but it's very manageable. Okay, so the way that we'll look for solutions is we'll look at numerical continuation methods. So here's our one equation. The unknown is eta and c, and we want to generate a bifurcation diagram. And so assume in general, since we're looking at periodic solutions, that well, you can show that solutions will be even, and so you can decompose it into cosine series. And then you can find where the bifurcation branch starts by linearizing, and so you get that c is equal to square root of, oh, I guess this should be d, sorry about that. And then you can figure out that your linear solution looks like a cosine. You use that, you plug it into the equation, then use Newton's method to compute the true solution, and then scale that true solution, plug it in again, and you get a higher amplitude solution, etc. So that's kind of what we do to get at solutions along this bifurcation branch. Except the only thing you have to worry about is if this also relates to what Emilian was discussing in terms of you have a minimum in your curve. So you have two different solutions that could travel at the same speed. So the way that I look at it is a resonance. So this is a manifestation of Wilton ripples that you have for gravity capillary waves, but in this case, just the relation is a bit different. So what happens is, at linear order, you obtain this relation. So you can do a plot. So depending on what your value of flexural rigidity d is, if you say that your linear solution looks like a cosine, you'll also have another higher frequency cosine showing up at linear order as well. And you can relate it by just doing a plot of this in terms of d versus k. And so what I'll often do is I'll vary d in order to get a particular Fourier mode to resonate with my first mode, my plane solution of a cosine. And so how does this look numerically is, okay, well, let's fix a depth to be 0.05. And let's say I want a resonance to come in at k equals 10. So these are also those generalized solitary waves that Emilian has mentioned, but just in a different parameter regime. And so, okay, so I start off with, for a pretty small amplitude, my wave profile looks roughly like a cosine, but I see when I look at Fourier modes of it, I see that there's kind of these peaks coming in at 10, 20, 30, and et cetera. So this is manifestation of resonance. So in this case, I picked a relatively small depth, and I picked a pretty small value of d, and I see that I have resonances for these periodic solutions. The other thing, too, is I actually plotted two different models. I plotted that linear model and nonlinear model for the flexural term, but they lie right on top of each other in this regime. So the interesting thing is there are these resonances, but they look the same for the different models we considered for the sheet of ice. So it's interesting because you have resonances. It's not really interesting because the models look the same. Okay. So let's look at infinite depth, just a different parameter regime. So for example, let's look at some small amplitude solution for the nonlinear model, which is in red, and linear model in blue. And let's change d to be 0.01. So we took h to be infinite. And you see, okay, the two bifurcation branches kind of lie on top of each other. So the blue and the red lie on top of each other. Okay, so then you pick a different d, flexural rigidity. Bifurcation branches go the other way, which is kind of interesting. So that means that higher amplitude solutions travel at slower speeds, whereas before you had higher amplitude solutions traveling at faster speeds. And then they start to deviate. The blue and the red start to deviate. Okay, and so pick a different d, 0.3. We made it larger. The flexural rigidity is larger now, and you start to see, okay, the bifurcations start to deviate more and more from each other. So that means that the nonlinear model and linear model for these larger flexural rigidity start to look different from each other. And then you pick another d to be 0.05, for example, and you just have different bifurcation branches going a different way. So in the linear, using the linear model for these flexural gravity waves, you see that the higher amplitude waves travel faster, whereas the nonlinear model says the higher amplitude waves travel slower, which is kind of interesting to see. Okay, so then let's look at exactly what these waves look like. So the wave profile, so despite the fact that you get different wave speed c for different amplitude, the wave profiles for the different models actually lie right on top of each other. So you don't really see this in terms of what the waves look like. The models give you the same thing, but the bifurcation branch, the wave speed that these things travel at are different.
How could two identical waves travel at different speeds? Like, how would you know which wave you are?
What do you mean?
You've got the surface is identical, so the force on them, like why are they traveling? I don't understand how they could travel.
Oh, like depending on the force that they have, why do they travel in different?
Well, if they're identical, why would they be traveling at different speeds?
Different equation.
It's you're solving a different equation, so you have a different so you have a different condition at the boundary. So you're either using the linear or the four derivatives, the eta 4x, for your condition at the boundary, or you're using that more complicated derivatives of curvature. But you're saying, like, physically, how do you know that?
Okay, yeah, I see what you're saying.
But the models are different, yeah.
Must be different.
All right. So, okay. So you can do also a few more things using that Abeles-Foucault-Mussolani formulation. So the beauty of that formulation is you can look at asymptotic models. So this is where I tried to, instead of only numerically seeing the fact that the different wave amplitudes go in different directions, I tried to asymptotically then derive an NLS, because it's valid for that infinite depth regime, to see, what I get out of the asymptotics. Will they give me the same thing? So in this case, we go back to the time-dependent equations. Actually, this should have, instead of minus infinity to infinity, this should have a period from 0 to 2 pi as the limits. And we'll just look at infinite depth and small amplitude solutions, because that's where NLS will be valid. We expand this up to order epsilon squared, and then you just introduce a change of variables because it makes things a bit simpler. And we'll look at solutions of this form. And so Emilian kind of already discussed this slow modulation solution. So eta 1 will be the term that it goes with e to the I theta, and then you have an epsilon perturbations of that have constant term, and the term that has a higher oscillations, and and then you can introduce multi-scale variables. So capital X is epsilon x, and et cetera. And so then what you do is you look at different terms of order epsilon. That's just the way that you usually do asymptotics, and then you group terms based on harmonics. So depending on so terms of e to the I theta, e to the 2 I theta, et cetera. So you plug all that in, and you group them, and then what you obtain is nonlinear Schrodinger equation for eta 1. And so here it is. And then, so the term multiplying the two derivatives of eta 1, it doesn't depend on the model. It just depends on the dispersion relation, which is the same for either model that you use for flexural rigidity. The only thing is that you have this k to the 4 multiplying d. But the term multiplying the nonlinearity depends on the model. So this is kind of where you'd even see asymptotically that the bifurcation branch is going in different directions. So the nonlinear model, that term m, that multiplies the nonlinearity is given by this, and the linear model is given by this. And so you can even see that k to the 4d, all of that squared, has a different sign in front of it. So as d becomes large, you see that this will have a plus and then a minus up front, and this will have a minus and minus. So this will be a plus, and this will be minus in the numerator. So you can even see when you're deriving the NLS for the different models that you're going to have different things happening. So the gray doesn't show up, but the regions of instability are in gray. So what I've done here is that the only thing that's different for the two models is that m, the value of m. And so I've basically plotted that m value. And so depending on m, and depending on your coefficient that multiplies your two derivatives of eta 1, you're going to have either focusing or defocusing NLS, and then you can talk about, then you can talk about stability, which is so the unstable region, which is the focusing NLS, and the stable region, which is defocusing NLS. So the unstable region is actually up here. So there's that line, and it's separated by this line, and then it's in that quadrant, basically. So that's unstable, and this is also over here is unstable. So the nonlinear model is in red, and the linear model is in blue. So for small flexural strength parameter d, the two models roughly change stability in the same area. But for large d, you have some deviations where a nonlinear model becomes unstable again for larger d, whereas your linear model becomes stable, and then it stays stable. Okay, so this should, we can also confirm this with numerics. Okay, so let's do some numerics and actually compute stability of these waves. So we'll
give me an idea what the D is when it's redimensionalized. I don't have a view of how big D is.
So I'm not sure I could give a very good. Emilian, do you have a? I could just tell you what D is in terms of Young's modulus and Poisson ratio, but I'm not really sure what the. You want physical values or?
Okay. Yeah, I mean I'm seeing 0.5, which is obviously non-dimensional.
Non-dimensionalized, yeah. So
I want to see, 6 times 10 to the 9 or something.
Well, it depends on your. It depends on the period that you pick for your wave. It depends on the wave height as well. So you have to introduce those parameters back in, and I haven't done that. So I'm not really sure. It depends on the type of wave that you end up getting. Do you have any?
I just want to be sure that you're in the sea ice regime. We're not looking at something like
That's fair.
some other material.
Yeah, so I'm not really sure how it goes back to the physical variables because I'll have to introduce a lot of the other dimensions in there. But do you have any No, because it'll depend on the type of, or the size of the period that I use and the height of the wave. But I'm not sure. I should do that. You're right. But I don't know if I'm in the sea ice regime or not. I just know they're different.
Because you've got this parameter of the period, you probably could find there'd be some overlap.
Yeah, exactly. It'll depend on exactly. Yeah, but I'll have to say, okay, for waves of period, whatever amount in meters, and yeah. Okay, so I'll just go on. So let's do this numerically. So we have the asymptotics for it. Let's try this numerically. We'll have to introduce some spatial averaging in the non-local equation, and then we'll perturb our computed solutions, which are Q naught and eta naught. So those are things that I showed you in the bifurcation diagram plots. Let's perturb them by something that has a particular time dependence, e to the lambda t. And then since we're doing periodic problem, we'll also we'll say that bounded solutions look like e to the I mu x, where mu is real, times some other eta 1 tilde or q1 tilde. And we'll use Fourier since we're in periodic setting. And then we substitute everything in, and we get a generalized eigenvalue problem. So now we have numerical values for eta and q that we got from the previous computation. And now we'll look for lambdas. So lambdas will tell us if things grow exponentially, that means they're unstable. If lambda is purely imaginary, things won't grow exponentially, so things are stable. And so let's look at this numerically and then see if we can recover the NLS regimes, which are purely asymptotic. The other thing we can do is we can not only look at where lambdas will give us something exponentially growing, but we can also then look at growth rates. So if we go back to, so what we'll get from the numerics is how lambdas look. And so let's go back to the asymptotics, the NLS, and then let's see also that let's do something similar. So perturb, we have to kind of change variables because NLS was in a different variables. So then we once again do the flow K expansion, plug that in, and then we can actually look at for how these things grow asymptotically in the NLS regime. So we get something like this, and we can see the maximum eigenvalues for this NLS will be m times a squared. So that's the amplitude. So now we'll be able to compare the asymptotics and the numerics. Okay, so let's look at linear and nonlinear models. Once again, the wave profiles for small amplitude look exactly the same. So I've plotted just 3 of them. And then on the right-hand side, I plot the flow K parameter, which will tell us what wave period leads to an unstable perturbation. And on the y-axis, I plotted the real part of lambda. So this will tell you if you have exponential growth for that particular perturbation. And so the linear model is blue, the nonlinear model is red, and then the first thing in the inside corresponds to the smallest amplitude solution, then you have a larger amplitude solution, you have a larger amplitude solution. So the dots are numerical solutions, and then they lie right on top of curves, so you can't even see the asymptotics. So now the asymptotics predicted by NLS match very well with the numerics. And so for this particular regime, d equals 0.01, you see that if you perturb your periodic solutions with a particular period determined by flow K parameter, you'll see that some of them are unstable. And then you can look at kind of what the instabilities look like by just plotting the imaginary part of the eigenvalues versus the real parts, and you can see that asymptotics numerics lie right on top of each other. And you can do that in a different regime, d 0.01, where your numerics and asymptotics start to deviate, for example, for the nonlinear model. And that's just because you need smaller and smaller amplitudes to stay in the linear regime. And so the asymptotics, the curves, give you asymptotics for small amplitude, whereas when you're doing numerics and you're doing it for particular amplitude, you'll start to see nonlinearities as well. So this kind of tells you that the nonlinear model, you're computing, you have to go to smaller and smaller amplitude waves in order to stay within that linear regime. But things fit pretty well, but they exhibit slightly different stability depending on the model that you're using. You can do that for a larger D. All right, so that's a bit about stability. So maybe in the next little bit, I'll just talk about some three-dimensional wave computations. So the reformulation that I'll use will be the boundary integral method. And here are the 2 models in 3D. So the nonlinear model is a lot longer in 3 dimensions, but that's all right. It's still manageable. It's just a very long term. Okay. So the system of equations that we're solving now looks like this. So you have 2 integrals now. They're over, they go from minus infinity to infinity because now I'm looking at solitary waves. And let's just write this down in infinite depth because it makes it a bit simpler. And so here now you have this equation parameterized by Froude number. I have a pressure in there as well, and you have an arbitrary condition for, you can put in what model you want to use. And then the interesting thing about the boundary integral methods, you have these 2 K1 and K2, so these are your kernels. And these kernels have this denominator D, which you can imagine could get quite small. All right, so you can also compute these symmetric waves. So if you introduce symmetries, you're just going to have more terms that you have to integrate over. So numerically, that's fine because you could just write down a function and then you could just take in whatever y or minus y or et cetera. So you can compute symmetric waves this way, and it'll just reduce the dimensionality of a problem by half. If you, for example, consider symmetry in y, if you consider symmetry in x and y, you can reduce down your problem to a quarter. And then you have to note that part of the integral is singular, and so you have to subtract it out. You have to subtract and add a certain part to make sure that you get rid of that singularity. So you introduce another term, and then one of the terms, you can actually compute it explicitly, so you can write down the solution to that integral, and that you can find more details in the Forbes paper. Okay, so let's discretize. And so for this computation, we just considered equally spaced points because it's a bit hard to motivate something that's not equally spaced because you don't really know what your wave profile is going to look like. So you could think of trying to concentrate your points, but it's a bit hard because you're going to have this nonlinear wave profile, so it's hard to figure out what kind of concentrations of points along where you can do. So let's consider equally spaced points. You have n of them in the x direction, m of them in the y direction. And so your vector of unknowns, since you're looking at 2 equations, will be q, which is the velocity potential derivative in x, and then eta derivative. So those are unknowns. You're welcome to pick other unknowns. You can pick q and eta. You can pick y derivatives or whatever. But this is kind of the simpler version for at least the gravity waves case. So your vector of unknowns is this. It's quite long. It's basically 2 times n times m. So that's a pretty big problem already. And then you're going to use finite differences on this regular grid to discretize the derivatives. So you obtain 2 times m equations. And you'll end up solving some problem that looks like g of u is equal to 0. All right, so you use Newton's method. So set up initial guess until convergence, solve this. So it's the same thing that you would do also in 2D, but you do this in 3D. It's a lot larger. But the thing, too, in 3D, it's a bit harder to come up with a good initial guess, and your Jacobian is very large. So this is why people sometimes use Krylov methods is instead of inverting your full Jacobian to get this result, you kind of set up an iterative way to compute the inverse. Okay, so the sparsity for the linearized Jacobian looks like this. If you imagine on the right-hand side, this matrix is going to multiply a vector that's composed with etas at first and then q's. And if you go back to your equations, sorry to go back so many slides. Right, so you see that in here you have this integral over q in there, and then I guess also integral over eta. And so that's where your dense part comes in. So that's this dense part because you have to integrate over your entire domain, and so that's the dense part of the matrix. This thing is actually the part that comes in from having that flexural term on the right-hand side, and then you have everything else. So you have, depending on the variables you use, you can kind of move around this dense part. So for example, if we're using a different formulation, so not the boundary integral formulation, but for example, if you're working in Fourier space, the Laplace equation in Fourier space is quite easy to write, but then you'll have a problem for your Bernoulli condition, because then you'll have to rewrite that in some different way. So you might be able to remove that dense part and put it up here or something, but you'll still have some part of your problem that's dense. Okay, so computing the Jacobian is the most computational intensive part. And there's two ways of kind of dealing with that. So either using an inexact Newton's method or a modified Newton's method. So modified Newton method is an iterative method, and then an exact Newton method is a direct method, but then you don't compute the exact Jacobian. So we've tried to use these two things. For the linear problem, it's kind of nice. You can use either method and it reduces. But when you're looking at nonlinear waves, you can't quite do these things very easily because you need a good initial guess, and you need a pretty good initial guess for a Jacobian in order to compute a nice nonlinear wave. Right. Well, you can't really quite see the gray, but imagine this is gray. So as Emilian mentioned, the thing that we do first is we compute the problem with the forcing, so that pressure. This pressure looks like this. And then once we get a bifurcation branch for the force problem, you can remove the forcing and you get the free solitary waves. But so far, I'll just show you the forced results. So this is the pressure. So the forced depression waves using nonlinear model, you get this bifurcation branch. And you can, so you start out with something that looks like this. And then as you get higher and higher in amplitude, it gets quite oscillatory. And then you know you're truncating this oscillation. So technically, you should have a larger and larger domain for these higher and higher amplitude waves. But I can't do that because it takes too long. But then once you get to a certain amplitude, these waves actually start to kind of become more like a lump. So they start to be, once again, gathered around here. And then you're reducing the oscillations more and more. So let's summarize that on this bifurcation diagram. So you start off with some initial solution that looks kind of lumped. And then you get these things that I know I'm truncating at. So at this part of the bifurcation branch, I'm not solving the real problem. I'm solving a truncated problem numerically. But then later on, you get, once again, to something that kind of looks more like a lump again. So then, even though I'm truncating things that have decayed. OK. So let's compare a linear and nonlinear model of bifurcation branches. Well, they look pretty similar. The waves look pretty similar, but the branches start to deviate. So in here, I've parameterized using Froude number. All right, so let's look at the linear and nonlinear model, compare the wave profiles. So this is for a pretty small amplitude wave. The wave profiles lie right on top of each other. There's not really a difference. And then you look at a higher amplitude waves. You have, this is some numerical, actually, deviations, but basically the wave profiles look quite the same. And this is what we expected. The same thing happened in 2D. The wave profiles look the same, but we had a different wave speed for them. In this case, that different wave speed is I've reparameterized using the Froude number, so we have different Froude number for these two different models. All right, so let's plot the whole thing. So these are the depression waves, and these are the elevation waves. Linear models in red, nonlinear models in blue. So they kind of lie on top of each other, but then they start to deviate. But the wave profiles look pretty similar. All right, so I guess in the last couple of minutes, let's conclude. So we can compute solutions to both models. And 2D and 3D, they produce similar shaped profiles for the different models, but at different Froude numbers or different wave speeds. The code is actually pretty easy to use and easy to modify. And we've been testing a variety of methods to make it faster. And so the future work is that we have to make sure that, I showed you that region where we truncate. We have to make sure that it doesn't matter what, that the solutions we get afterwards that look more like lumps, it didn't matter that they came from a region where we truncated more or less. We have to make sure that they converge to the same solutions for higher amplitude. We've done a little bit of that, but not very much. And then we have to compute accurate free surface waves for both models as well, which I haven't been doing because I still haven't analyzed the convergence very easily. So I want to make sure that the starting guess for my free waves without the forcing is the same, no matter what the truncation is. And then we just have to make sure that, Emilian discussed this already, but to see that do these waves bifurcate from zero, in depression or elevation case, what he saw was they don't, so we have to look at that more and make sure that we go to the smallest amplitude that we can, which is a bit hard. All right, thank you very much.
Thank you, Olga. Are there any questions? One over there.
Two comments. The first comment regarding the question would be, so a quick calculation I did for a 10 centimeter of the ice sheet that gives a bead in order of 10 to the power 6.
10 to the 6, okay.
Yeah.
So it's
30 centimeters that give 10 to the power 7.
okay.
Sorry,
But I have
I
to-
can't hear what you said. Can you say it so the audience can hear what you're saying?
Yes, for I sheet of thickness 10 centimeters, D equals dimensionally equals to 10 to the power in the order of 10 to the power 6.
10 to the power 6.
Yes, and for 30 centimeters, that's 10 to the power 7.
Okay.
So I'm going to have to relate that to my non-dimensional D. But yeah, okay, perfect.
Thank you.
Thank you.
The other comment regarding the Fourier mode that you showed.
Yeah.
In one of the plots, actually the numbers there 10 to the power minus 10, reaching 10 to the power minus 10, very small numbers.
Oh, which when I was in here, or
One of the first.
like in the two
figures that you
dimensions?
showed. Yeah, just like here. But it makes sense to introduce a small parameter, physical parameter, which is related to psi, right? And then rescale the whole thing. And then you would avoid having those small numbers, and at the same time that would give physical meaning also to.
So which are the small numbers that you're talking about?
So you have the Fourier mode.
Yeah. So like on this plot.
Yes.
So this is the amplitude, the size of the Fourier. So yes, I could rescale but to me, small amplitude solution means my. So yeah, I have an epsilon multiplying my first Fourier mode, so that's a very small number.
But what is the physical meaning of epsilon?
Wave amplitude, but it's been rescaled as well.
Okay, correct.
Yeah. Yeah, so I want that epsilon to be small because then I do some asymptotic comparison as well.
Yeah,
But yeah, it has.
Oh, another one here.
I have a really, really simple question.
I hope I have.
Embarrassingly simple. I don't understand what you mean by the bifurcation there. Like, what is what's bifurcating?
Right. So, so this is kind of interesting because somebody in a different field said, well, this isn't really a bifurcation diagram because the way that they think of a bifurcation branch is that at every point you have a bifurcation. But for us, it's just at the bottom you're bifurcating. So I could either have waves here, or I have this c squared, basically. So I could have. So basically, my bifurcation point is down here. So I'm bifurcating off. I have a zero solution, which is valid, and then there's some solution that's non-zero.
So it's like you've taken the solution for very small amplitudes, and then you've tracked where that solution moves as you increase the amplitude.
Yeah. So the bifurcation point is here, and then we call this bifurcation branch, but there's not really further bifurcations along that branch that we know of, at least. So yeah. So but the bifurcation point is right there at the linearized. That's what we get by linearizing. That's where we find the bifurcation point. Yeah.
Yeah, I'm not sure bifurcation is the right term there.
So it depends on the field that you're in. So we call this a bifurcation branch. A friend of mine who listened to this, who's in computational neuroscience, said what I would call a bifurcation branch is if you have a bifurcation at every point of that branch. But that's just terminology. Some people might know more about this because but I don't know. Yeah.
Because it's commonly used, it's probably worth explaining because it's used commonly in nonlinear to distinguish between you get a change in the behavior of the solution.
Yeah, so the bifurcation point is down here, but then we call it a bifurcation branch because it comes out from this point.
Isn't it a flat solution?
Yeah, exactly. So the flat solution's along the.
From the flat solution?
Yeah, exactly.
And the wave is a non-linear perturbation of the flat solution, and it's a bifurcation from the flat solution, which exists for all speeds and all parameter values.
Oh, okay. I see how you think of it.
Yeah, so the trivial solution's along the axis.
Okay, because that's the amplitude you're plotting there. Ah.
Yeah, sorry. That's probably something I didn't explain.
Yeah, no, I get it now. Okay, that makes more sense.
Anything else? Okay, let's thank Olga once again. Thank you very much.